Yes.
Hello everyone, and can you hear me? Can you hear me?
Yes. Yes, we are here, but please increase your volume.
Hello everyone, and welcome to my presentation. This talk is about holographic superconductivity from four-dimensional Einstein-Lovelock theory. Let's first take a look at some minimum ingredients to realize superconductivity. The first is diverging conductivity or zero electrical resistivity below a critical temperature. As shown in this figure, for a typical superconductor, we observe that below a critical temperature, the resistivity suddenly drops to zero. But for a typical metal, a regular behavior is observed. The second one is the London.
Sorry, I think your voice is not understandable. It's very low. Could you touch more powerful?
No. Microphone is maximum. No. I have some limited access. No.
No problem. Speak louder. Just speak louder. Your system is okay.
Continue.
Continue.
From the beginning or continue?
Just
Okay. And the third one is the existence of an energy gap, as will be explained in a moment in this talk. This here story, as the first microscopic theory of conductivity, has these ingredients. But as it is obvious from the context of this conference, we are interested in holographic phenomena. ADS-CFT correspondence claims that strongly coupled quantum field theories can be understood in terms of the coupled ADS-CFT fields. The left-hand side of this famous relation is the function of gravity or Mach theory, which is by saddle point approximation. This bar here is region action, and phi denotes field propagating. This field, any field in the bulk, acts as a source in the an external source boundary theory. The right-hand side of this relation is Gaussian propagation theory, in which we have a source and a boundary operator as a source. All of these schematically can be illustrated by this cartoon. Here we have a black brain asymptotic region, lower dimensional boundary theory. Using this relation, it's inferred that one can find response or boundary operator as shown here. Some examples are summarized in this table. The bulk fields are dimension with external sources. For superconductivity, we need Maxwell field and scalar field as the order parameter, and these must present in our action matter. The simplest and the first model of holographic superconductors consists of Einstein gravity minimally coupled to vector field and scalar charge scalar field, in which square mass scalar mass charge. The holography black-brain background is Schwarz which fields can create. Or this is the probe limit where the back action matter fields. The background, one can change the background or modify the matter fields to achieve richer physics. And here we would like to examine a new background which comes from the four-dimensional limit of Lovelock gravity, generalization of Einstein gravity in 3 or 4 dimensions, and coincides with Einstein gravity, but in higher dimensions we see that quadratic and cubic terms and more higher correction terms are appear. But in the view of gauge gravity duality, these higher curvature terms cannot affect the physics of 3 or 4 dimensional boundary field theory. To circumvent this issue, one can use the 4-dimensional limit of Lovelock gravity. The first version of this proposed by Lavan and Lane in this reference, in which the 4-dimensional Gaussian gravity was proposed. This can be done by first rescaling the Gaussian coupling as is, and then taking the 4-dimensional limit of the resulting field equations. This pattern can be extended to higher dimensions for cubic terms and also for the rest of higher curvature terms. And using this approach, all the higher curvature terms of gravity can contribute to the 4-dimensional Einstein. Different regularization procedures of 4-dimensional Lovelock gravity have been presented. Here is the background. The black-brain background we consider here is a solution to some of these regularization techniques. In fact, we use a black-brain background in which the coupling are finely tuned as up to curvature corrections. It is a solution to this naive theory, and also is a solution to the regularized for the Holographic reduction of this theory, and it is conceivable that it can be obtained from the conformal regularization approach of this theory. So this is a very interesting background to investigate the effect on conductivity boundary theory. Some properties of the black-brain background are listed here. This solution approaches the Schwarz for small values of coupling here. asymptotic behavior of the solution here, which constrain the Lovelock coupling here. And using this, one can define an effective cosmological constant. Yes, the temperature of black brand or the boundary field theory is simply obtained. Now we turn our attention to the superconductivity of and the boundary theory. As usual, we consider a vector and complex scalar field in the Bach theory, and using static and homogeneous constants by varying this Lagrangian, we find scalar field and vector field equations. These two coupled equations have to be solved by imposing some boundary conditions, horizon and boundary. At the horizon, we demand that the norm of a vector field be finite, so we impose this condition, and from this, I forward in this. At the asymptotic region, these two coupled differential equations can be easily solved, and for the pH potential and scalar field, where the scaling dimensions are given by this relation. From this radical, one can obtain the EF bond, and from the positivity of the delta minus, square mass should be negative. So, putting all these together, we can fix square mass equal -2, and from this one, we can find the allowed range of Lovelock coupling. The normal and superconducting states can be identified with two different states of black holes, black hole background. For high temperature state, there is no condensate, so we set scalar equals 0, and the normal state would be a charged ADS black hole solution. On the other hand, in superconductors, at temperatures below the critical temperature, we expect the system to have a spontaneous condensation without external source. So it is observed that regular solution with a non-zero scalar operator is found only for temperatures below a certain critical temperature. In conclusion, the superconducting state can be identified with a black hole having a non-zero scalar. We should emphasize that in the view of ADS CFT correspondence, either of psi plus or psi minus can be dual to the expectation value of a scalar operator boundary, and the other one would source, and during superconducting state, we should turn off the source to have spontaneous condensation. Here, considering the psi minus as the source, the psi plus is the condensation, boundary operator, and we plotted the condensates of the scalar operator as a function of temperature through cubic curvature for different values of coupling. Here, the solid black line represents that of general relativity, and the effect of the higher curvature of obvious here. This region belongs to positive. The critical temperature for the scalar operator as a function of double coupling here, and shown seen here as Lovelock coupling increase, the critical temperature. Now we can interchange the role of the source and the boundary operator, and we again see that below a critical temperature, condensation suddenly starts here, but there is different. The details are different. For example, for at extremely low temperatures, the condensation occurs. This shows that the probe limit doesn't work well here. And contrary to the previous case, as the Lovelock coupling increases, you see that temperature now we can discuss the conductivity of the boundary theory to investigate the effect of higher curvature connections on the conductivity. We add external electromagnetic radiation by inserting this into the Lagrangian perturbative vector potential. We obtain this solution, and the current on the boundary is obtained here using Ohm's law, and then Hugo formula from the linear response theory. We can depict conductivity versus frequency. This is frequency over critical temperature, and for the Einstein gravity, we observe universal ratio, this ratio, but for Lovelock coupling having positive values, we see greater values, and for negative coupling, we see smaller. As a summary, we presented the first construction of Lovelock holographic conductors with curvatures. We found that it is a sensible holographic model. It is also observed that higher curvature connections make the deviation of the universe frequency over critical temperature greater. For positive values of Lovelock coupling, higher curvature connections make the condensation gap larger. This means the scalar here is harder to form as increasing the coupling, but we can, in principle, we can build 3D Lovelock holographic superconductors up to any order of higher curvature connections. Have a sense for situations that infinitely higher curvature terms are. For this, we already built the background for this purpose, finely tuned background, which is higher order corrections. And it is considerable importance to investigate the competition between Gauss-Bonnet and third order Lovelock, study the effect of the general background on the phenomenon of holographic superconductivity. Background have been constructed as reference. Until now, our study was limited to slave holographic superconductors.
Thank you, Ali. As the time is finished, if anyone has question, please ask in chat box, or you can continue in the discussion room.
Thank you very much. Questions?